All right, geometry. We're in lesson 23, base angles of isosceles triangles. If you remember, an isosceles triangle, that's awful. An isosceles triangle has two congruent sides and therefore two congruent base angles. That's one of the definitions of isosceles. So we're going to talk a little bit about that today. First of all, let's talk about a few examples in our opening exercise. Describe the additional piece of information needed for each pair of triangles to satisfy the SAS triangle congruence. So let's mark this up. If we know that AB is equal to DC, what else do we need to know if we want to prove that ABC is congruent to DCB? Okay, if we see they share the same base, so I can say that they're congruent. But I need to know about these angles. Okay, what I would often do when doing a problem like this for the first time, I would sort of pull those two shapes apart. We know these are congruent. That's the reflexive property, remember? We just need to know about the angles. Okay? So basically, we would need to know that the measure of angle B is equal to the measure of angle C. But we could also, they could give us information like AB is perpendicular to BC, because if they're perpendicular, it's 90 degrees, and DC is perpendicular to CB, because if they're perpendicular, they're 90-degree measures, which would mean that they're equal in measure. Okay, let's look at B. So given AB, which is the long side, it's going to be hard to mark that they're congruent, so we'll just write a red line over it, is equal to RS. And we also know that AB is parallel to RS. So they're equal in measure and they're parallel. Okay, what else would we need to know? We would need to know that this side is congruent to that side, so that would be CB is equal to TS. Or we'll do it in blue. This side equal to that side, which would be AC is equal to RT. What's important is that if the lines are parallel, we have to use that information to say that angle A, the measure of angle A, is equal to the measure of angle R, or the measure of angle B is equal to the measure of angle S, because they're parallel lines. That's corresponding angles, remember? So if we were to use angle B and angle S, we would need to use side TS and side CB. If we were to use angle A and angle R, we would need side RT and side AC. All right, today we examine a geometry figure, or a geometry fact that we already accept to be true. We are going to prove this known fact in two ways. First of all, by using transformations, and second of all, by using the side angle side triangle congruence criteria. Such a wordy little title. Here's an isosceles triangle ABC. We accept that an isosceles triangle, which has at least two congruent sides, also has congruent base angles. Label the congruent angles in the figure. Check. Now we prove that the base angles of an isosceles triangle are always congruent. Okay, so this is how we prove it. We are given an isosceles triangle, ABC, with AB equal to AC, and they are marked right there. We're trying to prove that the measure of angle B is equal to the measure of angle C. So draw the angle bisector, AD, ray AD, of angle A, where D is the intersection of the bisector and BC, and base BC. We need to show that rigid motions maps points B to point C and point C to point B. Okay, so first we're going to do a reflection. So let R be the reflection through AD, line AD. So we're reflecting along this line. Through the reflection, we want to demonstrate two pieces of information that map B onto C and vice versa. So first of all, we have ray AB maps to ray AC. And secondly, segment AB maps to segment AC. So ray maps to ray and segment maps to segment. Since A is on the line of reflection, line AD, the reflection of A equals A. If I reflect A on the line of reflection, I get A. Reflections preserve angle measures, so the measure of the reflected angle R along angle BAD. So if we, the reflected angle, the reflection of angle BAD equals the measure of CAD. So this angle maps onto that angle. Therefore, the reflection of ray AB equals ray AC. AB equals AC. Reflections also preserve lengths of segments. Therefore, the reflection of segment AB still has the same length as segment AB. So AB equals AC. So the length of the reflection is also equal to AC. So the reflection of B equals C. Using similar reasoning, we can show that the reflection of C equals B. Phew! Reflections map rays to rays. So the reflection of BA equals CA. So the reflection of ray BA up there equals ray CA. And the reflection of ray BC equals the reflection of CB. Excuse me. This one was in your last test. I can reflect that ray onto that one. Since reflections preserve angle measures, the measure of the reflection of angle ABC is equal to the reflection of measure ACB. Right there. We conclude that, finally done, the measure of angle B equals the measure of angle C. Equivalently, we can say that angle B is congruent to angle C. In proofs, we can state that base angles of an isosceles triangle are equal in measure, or that base angles of an isosceles triangle are congruent. We did all of that to be able to say these two things. Actually, the one thing stated two different ways. All right, let's try one. So, prove base angles are congruent with SAS. So we're not trying one, we're proving the same thing in a different way. So given isosceles triangle ABC with AB equal to AC. Okay, that's how we know it's an isosceles triangle. Prove that angle B is congruent to angle C. So construction, draw the angle bisector ray AD of angle A, where D is the intersection of the bisector and BC. We are going to use this auxiliary line towards our SAS criteria. Okay, so we're going to use it. First of all, we know that AB equals AC because it's given, and we know that AD equals AD because of the reflexive property. I always tell every one of my students, if you have two triangles that share a side, mark them congruent. Okay, we know that the measure of angle BAD equals the measure of angle CAD because we actually bisected it. Definition of angle bisector. Therefore, we know triangle ABD is congruent to triangle ACD because of side angle side. And to the important parts, because we know the triangles are congruent, we can say that the angles are congruent. Corresponding angles of congruent triangles are congruent. We're going to say corresponding parts of congruent triangles are congruent. We had a different CPCFT before, but this is corresponding parts of congruent triangles are congruent. You can say angles, but if we use CPCTC for everything, that'll account for sides, segments, angles, everything. Cool. All right, let's try another one. So let's mark what's given. JK is congruent to JL, and JR bisects KL. So we just did JR bisects KL. Prove that JR is perpendicular to KL. Let's write down what's given. JK equals JL. Given angle K is equal to angle L. We just proved this. Base angles of isosceles triangles are congruent. KR equals RL. Given? Well, it's definition of segment bisector, so it's not really given, it's a definition. I marked it. Definition of segment bisector. So we know that triangle JRK is equal to triangle JRL because of SAS. Therefore, we know that angle KRJ is congruent to angle LRJ because congruent parts of congruent triangles are congruent. And we know that those two angles, I'm just going to label them 1 and 2. That's a 1. Angle 1 plus, hold on. The measure of angle 1 plus the measure of angle 2 equals 180 because it's a linear pair of angles. If I substitute, so we're going to say this is angle 1. I can substitute that in and say that 2 times the measure of angle 1 equals 180 degrees by substitution. So I can say, oops, that's an angle. Excuse me. The measure of angle 1 equals 90 degrees, right? And that means that JR is in fact perpendicular to KL. This would be the division property of equality, and this would be the definition of perpendicular lines. That was a long one, but not extremely difficult. Okay, another exercise. In my notes, this looks like the last exercise. Oh, sorry. Let's look ahead. So this is number 2. Let's see what else we have. Okay, let's try the next one. Now, this is example 2. We actually have 5 examples, and they're all proofs. As you feel more comfortable, you don't have to do each of them in the lesson, but they may or may not show up on an assessment in the future. Just want to give you warning. And so I would listen through them and make sure you know how they work. You guys are getting much better at proofs, but they still take a lot of time to figure out. So I'm going to go ahead and talk through this one, and hopefully we'll get done sooner than later. Okay, so given AB equals AC and XB equals XC, we need to prove that AX bisects angle BAC. So AB equals AC. I'm going to go ahead and mark that. And XB equals XC. We want to prove that AX bisects BAC. Cool, let's write down what we know. So AB equals AC, that is given. And the measure of angle ABC is equal to the measure of angle ACB. And that's because they are base angles of an isosceles. Okay, we also know that XB equals XC. That was given. And the measure of angle, hold on, XBC is equal to the measure of angle XCB. And that is also because of base angles of an isosceles are congruent. Awesome. So it's going to be hard for me to mark that here, but I know that this angle is congruent to that angle. Let's see if I can change colors. And this angle is congruent to that angle. Awesome. All right, what else do we know? Let's see, if I look at the measure of angle ABC, I can say that it's equal to the measure of angle ABX plus the measure of angle XBC. Okay, that just says that this angle is equal to this angle plus this angle. Let's do it again for the other side. Measure of angle ACB is equal to the measure of angle ACX plus the measure of angle XCB. And that's just the angle addition postulate. Which is very cool. Okay, let's subtract stuff from both sides. So what I'm going to do is just subtract, do some algebra. Let's see right here. I want to solve this equation for ABX. So I want to solve it for ABX and for ACX. Okay, if I can solve them, that just means I'm going to subtract from both sides of the equal sign. Let's do this one first. I get the measure of angle ABX equals the measure of angle ABC minus the measure of angle XBC. And then this one's next. Measure angle ACB. Nope. See, I move slow because I don't like making mistakes, which I do all the time. Measure of ACX equals ACB minus XCB. And that's just the subtraction property of equality for both of them. Cool. Okay. With that knowledge, I can actually say that those two are equal. Up here I have the measure of ABC equals ACB. So I can substitute. ABC equals ACB. And right here, let's get blue, I have XBC equals XCB. So these are these two right here. So those are all equal to each other. We can actually say that these two are equal to each other. Measure of angle ABX is equal to the measure of angle ACX because of substitution. Let's see if I can get another color. Let's do purple. So we just did ABX, this angle, and that angle are equal. Cool. So now, if I look at side, angle, side, this triangle right here, and this triangle right here are congruent because of side, angle, side. Let's write that down. Triangle ABX is congruent to triangle ACX because of side, angle, side. I need a new slide. I hope you're following along. And since those are congruent, you can say angle BAX is congruent to angle CAX because of CPCTC. Corresponding parts of congruent triangles are congruent. Therefore, AX bisects angle BAC because they're equal. Definition of angle bisector. Phew. Let's try the third one. Given JX equals JY and KX equals LY, let's prove that triangle JKL is isosceles. Okay, let's write down what we know. I've got JX equal JY and KX equals LY. So these are congruent, those are congruent. That's given. Actually, that's not right. Let's mark the right things. I'm going to mark it in a different color so I can see better. Those are congruent, and those are congruent. Okay, it looks like I have an isosceles triangle here, so let's go ahead and talk about the measure of angle 1 being equal to the measure of angle 2 because of base angles. Cool. All right, measure of angle 1. Okay, let's do a little bit of addition and subtraction. If I can say 1 plus 3 is 180 and 2 plus 4 is 180, then if I subtract them out, I think I can say that 3 is equal to 4 because 1 is equal to 2. Let's say that again. 1 is equal to 2, and if I add these two together, say they're equal to 180, and these two together equal to 180, subtract away 1 and 2, I think we can say that 3 is equal to 4. So let's try it. Measure of angle 1 plus the measure of angle 3 is 180. For the same reason, measure of angle 2, measure of angle 4 is equal to 180 because they're linear pairs. Linear pairs are supplementary. Awesome. Okay, let's go ahead and do some subtraction. So the measure of angle 3 equals 180 minus the measure of angle 1, and the measure of angle 4 equals 180 minus the measure of angle 2. Subtraction, property of equality. And since 1 is equal to 2, I can substitute and say that the measure of angle 3 is equal to the measure of angle 4. Let's go ahead and mark that. 3 is equal to 4. Now it looks like I have side, angle, side. We'll keep it in blue. So I have side, angle, side. for that little triangle, and side angle side for that little triangle. Triangle JKX is congruent to triangle JKXJLY because of side angle side. Therefore, JK is equal to JL. JK right here is equal to JL because of CPCTC. Therefore, triangle JKL is isosceles. Oh goodness. Let's try that again. Isosceles because of the definition. Phew. Okay, number 4. Okay, we've got 3 and 4 left, or 4 and 5 left. So given triangle ABC with the measure of the measure of angle CBA is equal to the measure of angle BCA. Let's prove that BA is equal to CA. So this is the converse of the base angles. So we know that angle B is equal to angle C. And let's just use that as angle B and angle C. Okay, I'm actually going to type this out, so give me a second. Okay, first, we can prove that segment AB is equal to segment AC using rigid motions. First, we're going to construct the perpendicular bisector L to BC. So here we have line L, which is perpendicular to BC. So it bisects it, so those are both equal. Okay? All right, note that we do not know whether the point A is on L up there. If we did, we would know immediately that AB is equal to AC, since all points on the perpendicular bisector are equidistant from B and C. So everything on here is equidistant from B and C. We need to show that A is on line L, or equivalently, that the reflection across L takes A to A. Okay, that's what we're working on. Let's see. All right, let R1 be the transformation that reflects the triangle ABC across L. Since L is the perpendicular bisector, R1 of B equals what? Okay, what's the reflection over line L? That shouldn't be 1, sorry. Line L of B. It's C. Let's fix this. And this. Apologize for that. Cool. And the reflection on line L of C equals what? B, of course. We do not know where the transformation takes A. For now, let us say that the reflection along line L of A equals A prime, because we're not sure. That's not an A there. I'll fix it. Oops. Awesome. Okay, are we good so far? So, since angle CBA is congruent to angle BCA, and rigid motions preserve angle measure, after applying the reflection about L, to angle BCA, we get that angle CBA is congruent to angle CBA prime. So we're there, right? Just have to tie it up. Angle CBA and angle CBA prime share a ray BC are of equal measure and A prime are both in the same half plane with respect to line BC. Hence segment, or no, ray BA. I like how it capitalizes that, that's funny. And ray BA prime are the same ray. In particular, A prime is a point somewhere, oh goodness, is a point somewhere on ray BA. Almost done. Likewise, applying reflection on line L to angle CBA gives angle BCA is congruent to angle BCA prime. And for the same reasons in the previous paragraph, A prime, oh goodness, A prime must also be a point somewhere on ray CA. Therefore, A prime is common to both ray BA and ray CA. The only point common to both ray BA and ray CA is point A. If you look at the names of them, that's what we mean. Thus, A and A prime must be the same point. A equals A prime. I'll fix this in a little bit. Last sentence. Cool. Hence the, oh goodness, I'm back in superscript. Last sentence, I said that, didn't I? The reflection takes A to A, which means A is on the line L, and the reflection over L of BA equals CA prime equals CA. Or BA equals CA. Check. Okay, hold on a second. See if I can fit this on here. Okay, it's a lot of words, but I thought it made much better sense to do it this way than to, I can't reach, to do it this way than to try to write it out. It's a good proof, and what's awesome is now that we've done the proof once, we can use it to prove other things, right? Trying to get that out of there. There we go. So now we can just use that information that once we know, this is really the point of me doing this one, once we know that we have a triangle with base angles congruent, we can say that, all right, therefore it's isosceles. Those are congruent and the triangle is isosceles, which is awesome. Last one. Is anyone else excited? I know I am. All right. Given triangle ABC with segment XY as the angle bisector of angle BYA, and BC is parallel to XY. Prove YB equals YC. So we're trying to prove that this is congruent to that. So if I look, like if I can prove these angles are congruent, then we can say those sides are congruent because it would be an angle bisector. But let's see if we can even do that. I'm not sure. All right, so let's write down what we know. BC is parallel to XY. Okay, that's given. Now let's look. If I have parallel lines, BC is parallel to XY. So these are parallel. I bet that's going to tell me some angles are congruent. These angles would be congruent because they're alternate interior. Awesome. Let's say that next. The measure of angle XYB is equal to the measure of angle CBY because they are alternate interior angles. Okay, let's look at angle XYA and angle BCY. Right here. XYA and BCY. Those are congruent also because of those parallel lines. The measure of angle XYA is equal to the measure of angle BCY. They're corresponding angles. Awesome. Now I think I can use substitution. Oh, we have an angle bisector. Let's look at that one next. So XY is the angle bisector of BYA. So we know that this angle is congruent to this angle. Let's say that. Angle BYX is equal, measure of angle BYX is equal to the measure of angle the measure of angle XYB. Oh, I already did XYB. XYA. Let's get these in the right order. We did XYA, so we'll do XYB. Definition of angle bisector. Now the measure of angle CBY is equal to the measure of angle BCY because of substitution, because we have some equal angles there. And now we can say YB equals YC because the base angles are congruent, so the triangle is isosceles. Awesome. Okay, long video, but a lot of proofs, which takes some time. Good work today. Okay, I'm